Okay, good morning, everybody. We are almost on time. We'll be starting in 5 minutes, or maybe 1 minute now. I think you hear me well and see well also. In any case, just a few rules before starting. If you want to ask your questions, please ask in the question and answer just above the raise hand here on the right hand side of the screen, and we'll be happy to answer you. You will find also this registration of the webinar on our YouTube channel. So afterwards, you don't need to take notes. Afterwards, we'll put on our YouTube channel. You search SRMTech on the YouTube, and you will see our YouTube channel. And you can find also some informations on our website, srmtech.it. And you will see a video of our company manufacturing the compressors. So now it's time. We can start. Okay, I will share the screen. Okay, SRMTech. Who is SRMTech? SRMTech is a company located in Italy. Okay, here we are. We can see our manufacturing plants. We manufacture compressors, semi-hermetic and open compressors for refrigeration and AC, running with natural refrigerants and standard refrigerant. We have two sister companies, one in Sweden and one in China. And by the way, the company in Sweden has invented the screw compressors many years ago now, 1935. And then we've sold this license to Maekawa, Howden, Carrier, Thermo King, and so on and so on. So we know quite a lot about screw compressors. We wanted to share some trends with you of the market because since a few years, we are seeing now these four trends. On the first hand, technical dialogue and support, because the customer do not want to buy a compressor only. He wants the best compressor for its application. And for that, he needs advice, support, and a close technical dialogue with our engineers. So we have a team of highly qualified engineers in order to help you to choose the best compressor for your application, and then to explain to your end customer why it's important to have this kind of compressor. The second trend is innovation, because the regulations are always more strict, and it's important to have a better efficiency, to be able to do the maintenance very easily, to not have problem in running the compressor during the entire life. So in innovation, we'll be presenting tomorrow and the day after tomorrow, also on this platform, two webinars, and I invite you to follow these webinars. One for RS5, which is a compressor with high innovation, able to do savings during the lifetime of the compressor. Very important for your end customer, big savings. And the day after tomorrow, we'll be presenting also an ammonia compressor with oil separator. So it's a bit a transition for commercial innovation and industrial compressors. Last but not least, we have also a wide range of models important for the customer because he do not have to switch between a customer, supplier and another. And we have from the very little piston compressor to open compressor, we have a very wide range. And we produce in Europe, in Italy, in order to have very short lead time. So the people present on this platform, this is the 8 member of our team. We wanted to present you always to give you the better advice, the best advice possible for your application. So Enrico Faccio is the CEO of SRMTECH, is responsible also for R&D policies. In the past, he was R&D manager in RevComp, compressor company, and power system, also compressor for air. Thomas Broglia, director, CTO of SRMTECH. In the past, he was R&D manager of Frascol, and he will be doing a webinar tomorrow also about RS5. Rudi Schauser is sales director for industrial markets. He has a past of general manager in Bitzer, Australia, and Asia. And also other members of the team, our colleague, CTO of SRM in Sweden, Peter Ziegler in Germany, myself, Jerry Lin, and also our colleague in Russia. So a few words about the applications. We have the refrigeration, so any kinds of refrigeration from commercial to industrial, chillers, process cooling, food processing, data center, and today we'll be talking about heat pumps. So I present you Mr. Faccio, Enrico Faccio. As I said, he's the CEO of SRMTECH, responsible also for technical development policy. He has a past of more than 20 years experience as R&D director in compressor companies. He knows very well about piston and screw compressors and has designed some compressors with very innovative technology. So I pass the word to you, Enrico.
Okay,
and,
Patrick.
It's your turn.
Thank you very much, Patrick, for the introduction, and welcome to everyone. My name is Enrico Faccio, and I would like to mention that if you have any request, you can write in the question and answer areas. Then at the end, we will look to which are the doubts and the questions. So let's go directly to the topic. Let's say we will see today our experience for the high temperature heat pump and the application of the high temperature heat pump with one of the refrigerants suitable, that is 1233 ZE. So we need to have a brief introduction of the heat pumps. So we can first of all differentiate between the various levels of various type of heat pumps. So first of all, for the people that doesn't know, the heat pumps can be defined very simply with like a heat engine that use a cycle, a refrigerant cycle to produce hot fluids. But in this family of systems, we can differentiate between the common heat pumps that everyone can find also at his household's installations, with a split installed in the houses, where these heat pumps normally are indicated like with the maximum level of temperature. When we speak of maximum level, normally we define the heat sink level that is about 80 degrees C. For above these values, we start to define the systems as high temperature heat pumps that commonly are defined the system that produce fluids up to 100 degrees C. In the very recent period, we have seen also that other system has been introduced to produce higher temperature fluids up to 160 degrees C. And these systems are defined like the very high temperature heat pumps. Yeah, the VEH, HTHP stands for very high temperature heat pumps. So when we start to evaluate the heat pump usage, we have also to investigate which are the applications. So normally we speak regarding the application in industrial levels. And industrial levels, of course, needs different levels of heat. So on these different levels, we can define low processes, low heat, low temperature processes with the temperature lower than 200 degrees C. It is typically demanded for processes like drying and dewatering, or the high temperature process heat with the temperature above 500 degrees C. Normally that involves cracking, reforming, and reduction. The point of this usage of the heat is that normally in industrial processes, the heat after being used for the processes is discarded to the ambient at a low temperature levels compared to the first one. So from the exergetic point of view, this industrial waste heat represents a very valuable heat source that normally is a level at levels between 30 and 70 degrees C. And of course, these levels are not useful for normal industrial heats, but these levels are above the ambient air temperature, for example. So this can be used, these waste heats, to produce a high efficiency system and to produce first levels energies or with the satisfactory levels of temperature to be used again. So the user of these systems, we will see also that there are many studies that investigates how much this system can contribute to the reduction of the emission of the CO2 into the ambient, and also to the reduction of the greenhouses. Just to mention that more or less 80% of the current greenhouse gases emissions can be attributed by the demand of the energy in the way of the production of electricity and production of the heat. So if you would like to just roughly evaluate which are the system where the heat pumps can be applied, these two tables, this is a table that is split in two sides. It indicates different system, and we just can see how many typical application we can have, where in this system are identified in the light gray, the system with the temperature up to 100 degrees C. Then the higher level of temperature with the middle level gray between 100 and 140, and the high temperature systems. So where we have to investigate are the levels, as we have said, in this session we'll see how are the application for the high temperature heat pumps. So we can see between 100 and 120 degrees C. So it's just also another indications that can give the idea how much of the energy is used. Let's say that normally it's identified like 19% of the potential demand of the industrial processes in between 100 and 150 degrees C. For the moment, we will not evaluate the applications above 150 degrees C because there are some limitations regarding the heat pump technology. So when we identify the heat pump process, we can very simply put our system in this graph that illustrates where it is positioned, starting from the ambient temperature, the waste heat level, and the process heat. The heat pump process is positioned exactly in this area that it takes from the heat source from the waste heat, and through the input of the electrical power, it produces higher level temperature fluids that can be used for the process heat. In this page also, we can see also another graph that illustrates the comparison between the normal process for the production of the heat that takes the primary energy to convert into process heat. Of course, we have some conversion loss to be considered. And on the right, we can see the systems with the heat pump application. Of course, we have the consumption of primary energy sources to produce the electricity. We have still here, we have some losses. But what is different is that the heat pump that is located in this level of the process take a significant part of a waste heat and it converted to the process heat. So when we define this system, we have to consider the efficiency of the system that is identified with the so-called coefficient of performance, that is this formula. That is the COP. It's the ratio between the energy produced divided the energy consumed, so the electrical energy. We can use this coefficient both for the cooling, so it's cooling COP, or for the heating power, so it will be called like heating COP. If we can have a look regarding the market. The heat pump is increasing, and I think that everyone has recognized how much the market of the heat pump has grown in these years. So when we just see deeply on the market, there are some several publications regarding the analysis, and some very with a high reputation analysis indicates some figures that we can take as a comparison. That is the global market of the heat pumps that was defined like around $53 billion in 2018, and this market is expected to grow up to $98 billion in 2025. So within this short period of time, we will have this market that will be mostly doubled, and with an annual growth rate of about 9%. Of course, heat pumps are used in refrigeration equipment for commercial, but can be used also for industrial. So when we see all around the world which are the areas, for sure, the Asia Pacific region is the first contribution location because of the dimension of the population and also the dimensions of the industrial fields. But Europe is and also is expected to be still the second largest contribution, because in Europe, 50% of the total energy consumption is related to heating and cooling levels of the energy. So we have seen also that some of the governments, and especially the European community, has pushed and also is incentivizing the usage of the high efficiency systems like the heat pumps. North American market also is expected to grow significantly, thanks also to the government that is encouraging the adoption of heat pumps. Latin America is also expected to grow in a satisfactory way, in a decent way, especially because of the support of the Brazilian market, that is one of the larger regional consumer for the heat pumps. At the end, the Middle East and Africa are expected to grow moderately because of the less needings of heatings, especially in the households. So in this graph, going forward in this graph, it is indicated the distribution of the numbers of heat pumps units produced compared to the capacity, to heating capacity, expressed like in megawatts. We can see how the most of the units are with the lower power, and this number of units is of course decreasing with the size of the system, also with the capacity. So this graph is summarizing this graph. Just some other figures. We can express that 88% of the heat pumps units below 10 megawatts of heating capacity consume 48% of the total cumulative heating capacity, while the remaining 52 is related to the larger systems that are only 12% of the numbers of the units. So the numbers, all the heat pumps is very significant, and where this will like to focus is on this area, so with a higher demand. Another looks to the market and also to the status of the art of the moment is expressed by this graph that show which is the positioning of the laboratory or experimental systems, and position the efficiency of the system, especially with the COP, compared with the heat sink temperature, so with the temperature of the condenser. We can see how much this is on how are distributed the COP, and we can see how the higher levels that we can reach normally is between 6 and 7 as a COP, while the lower is between 2 and 3. What also is indicated by this graph is that the lower temperature lift is so-called the temperature lift, the difference between the evaporating and the condensing temperature. The lower temperature lift systems can grant the higher efficiency, while the higher temperature lift system between 60 and 70 degrees Kelvin, it's related to the lower COP, so with a lower efficiency. What also is necessary also to go in the evaluation and also in the design of the heat pumps, it's the selection of the refrigerant, because as we have seen, these are refrigeration systems that are using these systems to produce heat. So when we have to select a refrigerant, of course, the most important thing is the thermal suitability. The refrigerant has to have high critical temperature, normally higher than 150 degrees C, in order to have subcritical systems in the cycle that is used for the heat pump. The refrigerant has to have a low critical pressure, normally lower than 30 bar because of the type of materials used for the heat exchangers. The pressure that stays still also it's very important, because it's necessary normally that at 20 degrees C, that is the common ambient temperature, the pressure in the system should be above the ambient pressure, so higher than 1 atmosphere or 1 bar. This is necessary in order to prevent during the standstill operation there could be some leakage from the ambient to the system, in the case that if the pressure will be lower than the ambient pressure. Lower pressure ratio is also important on the selection of the refrigerant, because low pressure ratio give higher efficiency of the system. What also is important in the same way for the selection of the refrigerant is that this refrigerant has to be compatible with the environment. So the ozone depletion potential expressed by the ODP value has to be 0. So the refrigerant now used cannot more have ozone depletion potential. The global warming potential should be as low as possible, normally lower than 10. And also has to be non-flammable and not toxic because of the safety of the application. Of course, these are not enough. We have to evaluate also the efficiency of the system with the refrigerant applied, the minimal superheat, the behavior of the refrigerant with the lubricant, availability on the market, and the low price. So we have to check several things. What we have done is that we can show in this, we already have made the selection, and in this table we can see a list of the refrigerant suitable for the heat pump operation. The red highlighted area are those refrigerants that are already banned by the Montreal Protocol because they have the ODP value, so ozone depletion potential, sensible, so they cannot more be used since several years. On the yellow highlighted area, we have the HFC that are the actual used refrigerant. These are going also to be banned because of their global warming potential that is not lower than 10. In the green area, highlighted area, we can see the new refrigerants that are coming into the market, like suitable for the heat pump operation. In this table, we have selected the 1233 ZDE because, according to us, it has some suitable features for the common heat pumps. So we know most of us are used to evaluate the heat pumps or work with the heat pumps, and knows that the R245FA is one of the most used, or has been one of the most used refrigerants in these systems. Because of the Kyoto Protocol and because of his value of the GWP, global warming potential, it cannot be used for the next future. So one suitable refrigerant can be the 1233 ZDE because it has a critical temperature of 165 degrees C and a critical pressure of 35 bars. It is a A1 type refrigerant, so it's not flammable and not toxic. And it has a very low ozone depletion potential, even if it contains chlorine. But the ozone depletion potential is so small that it can be considered like a zero. What is also important for the 1233, it has that it also has long-term thermal stability and thermal performances. This table is comparing the main figures of the two refrigerants. So the critical pressure is very similar between the 1233 and 245. The critical temperature is also similar. Boiling point is also similar, and all the rest it's an advantage for 1233. So, which are the solutions that SRMTec can offer? We have mainly, we are considering this range semi-hermetic screw compressor. These are a compact type, so with integrated oil separator. And we have two different series. The other series is a heavy-duty compressor series with a nominal power between 40 and 390 horsepower, with a working pressure up to 28 bar. The second series that we can promote is the ES3 series, suitable for lower pressure ranges, still with a larger range of displacement, and they can express a little higher efficiency in the application range. In the SRMTec, we have full-featured testing facilities. We have 4 testing benches for capacity between main, especially like displacement between 20 and 1,500 cubic meter per hour. And our systems are designed in order to deeply evaluate the behavior of the compressor. So we use superheated cycles in order to be very flexible in the change of the parameters. And just for your information, with this system, we can change independently evaporating temperature, condensing temperature, and also the superheat. This permits to us to really map the behavior of the compressor in the very wide application envelope of different conditions. So our system that where you can see here the scheme of the system, it's using a non-common system because, as I mentioned before, we're using the system with the compression, then the cooling and expansion without having the condensation and also without having the evaporation. So it is superheated cycles. And by changing these values, we can modify evaporating, condensing temperature, and superheat. This is the scheme of the system that is using the ISO 917 systems. And as I say, this is very suitable for us to completely map the compressor. Of course, we have to make some assumptions, such as the heat dissipations by the pipes and heat exchangers, because we are mapping only the compressor. So we ignore this dissipation. The pressure drops in the evaporation and condensation processes we consider as negligible. Sorting process we consider to be isenthalpic, so with the same enthalpy. Refrigerant we consider and we simulate the refrigerant in order to calculate the capacity. Like it has been 5K subcooled liquid, and the superheat normally is taken at the 10K. So 10 degrees Kelvin. When we make the testing different from this value, normally we declare these values. So we do the testing with a procedure that it takes and it fixes the condensing temperature at a value between 80 and 110 degrees, changing it at the steps of 10K. And during the fixed condensing conditions, then we change the evaporating temperature at the steps of 5K between 20 and 60 degrees C. Compressor for the normal testing is maintained at fixed speed, so at 50 Hertz, but it can also be used with inverter with different frequencies. In the evaluation of the efficiency of the compressor and so of the system, we have to mention regarding two efficiency factors that we normally use. So the first one is the isentropic efficiency. That is the ratio between the multiplication of the suction density multiplied the real displacement multiplied between the isentropic difference between the discharge and the suction levels through an isentropic process divided by the electrical input. The second one is the volumetric efficiency that indicates how much of the how close is the real displacement to the nominal displacement. So of course, if it's not clear, you will have this publication later, so you can see also these parameters clearly indicated. But let's go to the test result that we have reached. So first of all, we have a graph that is showing the isentropic efficiency of this compressor testing, that is a series RS3. The size is 140 horsepower. This compressor is indicated like a nominal displacement of 402 cubic meter per hour at 50 hertz. So this graph is showing on the x-axis the pressure ratio, and on the y-axis is showing the isentropic efficiency. This is typical for the screw compressor to having a peak that is very good. So we can define that these compressors are performing in a good way with the 1, 2, 3, 3 refrigerant. And the shape smooth is also indicated that the testing are made in a satisfactory way. So they are not like a wave, but they are in a smooth way. They're smooth shaped. In the same way, also the volumetric efficiency still expressed in with the variant or the pressure ratio. Pressure ratio is the ratio between the discharge and the suction pressure. Still, the volumetric efficiency, it's showing this typical shape for the screw compressors with a higher levels that is very close to 1. So also from the volumetric efficiency point of view, we can define that the 1, 2, 3, 3 is also a good refrigerant applied with the screw compressors. This additional graph, it is showing the cooling capacity of the system, where here on the y-axis we have the evaporating temperature expressed in Celsius degrees. In the y-axis we have the cooling capacity expressed in terms of kilowatts. So these different curves express the cooling capacity at different condensing temperatures, so between 80 and 110 degrees. Of course, the cooling capacity at 120 is lower than at 80 because we have major losses or lower efficiency in the compressors. In this graph, it is showed from the other side the input power that indicates on the reverse that the input power increase with the increasing of the condensing temperature. This is why, because the condensing pressure is much higher than at 120 degrees than when it is at 80 degrees C. So this graph shows most of the results on the compressor, that we use the results to make the comparison between the 245FA and the 1233 ZDE data. So we have these first two graphs that are, this first look is made by maintaining fixed the evaporating temperature at 50 degrees C and varying the condensing temperature between 90 and 120 degrees C. We have the graph on your left that is showing the cooling capacity, and the graph on the right that is showing the input power. The first look can indicate that the cooling capacity of the 1233 is lower than those that expressed with the same compressor with the 245FA. This difference is about around 12% less lower. On the same way, also the input power is lower for 1233 ZD. So in terms of efficiency of the system, we have that the cooling COP it is higher on lower condensing temperature for the 1233. So we can see here on these two graphs that at 19 degrees C condensing temperature, the COP for the cooling COP for the compressor, it's higher for the 1233. That this difference is reducing, and there are practically no differences at 120 degrees C. On the right, we have the heating COP comparison. In the same way, we have higher heating COP for temperature, condensing temperature of 90 degrees C for the 1233, and the same way the heating COP is practically the same at 120 degrees C. So this first look already confirmed that the 1233 can be a replacement for the 245 because it has or equal or even higher efficiencies than 245 FA. The second look of the testing results, it is made by maintaining fixed the condensing temperature and varying the evaporating temperature. So we have a look at lower evaporating temperature, the cooling capacity is practically the same and is going to be decreased at higher evaporating temperature. In the same way, also the input power is lower for the 1233. In terms of efficiency, still the two graphs are showing the heating COP and the cooling COP. It shows how these values are practically the same at fixed condensing temperature of 110 degrees C. Another confirmation that the 1233 can be a replacement for the 245 FA. In terms of application envelope, these are the application envelopes of the compressors for both refrigerant that are quite similar in terms of condensing temperature. They both can run up to 125 degrees C for this compressor series. While in terms of evaporating temperature, the 245 can be used also at 15 degrees C, while the 1233, the minimum evaporating temperature, it's actually at 20 degrees C. So this it's what is important for the compressors. But we have made also an evaluation how we are positioned in the market in the real system. So this graph shows a map of the efficiency of the heat pump system produced by different manufacturers. Of course, on the axis we have the temperature lift, and the y-axis we have the efficiency of the system. This system, the COP, is decreasing with the increasing of the temperature lift, as we already have seen before. The results that we have reached, if we consider the 60 degrees K of temperature lift, the results is positioning our results in the top higher levels. Even if we are not considering in this moment the pump's consumption of the system, because we are considering only the compressor, this is showing that even if we would consider the absorption of the pumps, the system is positioned in a very good way, as I mentioned before, in the higher levels of efficiency. Of course, these are just a few of the looks of the application. So in the case that you need to evaluate the performances of the compressor or the application in different conditions, the best way is to use the SRMTECH selection software, where you can have the two refrigerants, and it is you will see what we have seen up to now in this presentation, this webinar. So just summarizing the results, 1233 express a higher COP, or at least same COP at 245 FA. They can be also, the COP can be also higher, over 10%. Testing results at fixed condensing temperature show that the COP is practically the same. And this confirms at the end that the 1233 can be significantly considered like a replacement for 245. We suggest for the usage of this refrigerant to use POE refrigerant because they are suitable for higher temperature compared to, for example, for the mineral oil. And as I mentioned before, the best way is to use our selection software that you can download from our internet site or by writing to us. So I hope that this even short presentation could be interesting for you. So I thank you for your attention, and I take just a few seconds to remind you that in the next days, tomorrow and the day after, we'll have other two very interesting webinars. The first one is about the application of the revolutionary system, that is the out-of-air system, presented by my colleague Thomas Broglia. And the day later, we'll have my colleagues, that is Rudi Schauser, that is sales director, that will present the application of a semi-hermetic screw compressor with ammonia. So other two interesting webinars for you that I ask you to follow. So thank you very much, and I don't know in this moment if there are any questions more.
Thank you, Enrico, for this very detailed presentation. Yes, we have some questions. One is for the refrigerant. And do you have in mind other refrigerant that could be suitable for this kind of application?
Yes, Patrick. We are of course investigating. What is important to do is to check the behavior of this refrigerant. But in our investigations, I just come back to my presentation. Just come back to the slides and on the table that is representing the list of the suitable refrigerants. It is very important, and in this list, while it is taking a very interesting or promising, very interesting result is the 1336 refrigerant that express higher critical temperature at a suitable critical pressure. And the first investigation made, it's indicated that this refrigerant is also very promising. So in the next months, we will also going to have some testing session with this new refrigerant, and I think that quite soon we'll come back with another webinar or another presentation to show the results with this refrigerant.
Okay, thank you. Yes, we have been a bit long. Yes, thank you for this presentation. I would like to highlight something. I think it is also very important, as I said before, to have a technical advice and to test the refrigerants. So we have the bench. We have usually what we do with the customers is that we are testing the compressor with the refrigerant in the envelope they want, and we can give the advice and also show the result to the customer. So this is quite important. Thank you very much for your attention. You will see this webinar online on YouTube. So you search for SRMTECH on YouTube and you will see this webinar. If you want some more information and be in contact directly with us, you can write to info.srmtech.it. Here you can see, and the website is srmtech.it. Thank you very much for your attention, and we hope to see you soon, maybe in the next days. Thank you very much.
Thank you very much.
Bye-bye.